next session on finite element analysis. In this session, we are going to discuss about the disadvantages of FEA. While FEA offers numerous advantages, there are also some potential disadvantages and limitations associated with its application. It's important for engineers to be aware of these considerations to use FEA effectively. Here are some disadvantages of FEA. Assumption of linearity. FEA often assumes linear material behavior and small deformations. In reality, materials may exhibit non-linear behavior under certain conditions and large deformations may occur. Non-linear analysis techniques are available but are computationally more demanding. There is a difference between linear and non-linear FEA. When we solve the problems in ANSYS, we generally assume that the problem is of linear type. Whereas in non-linearity, there are various other options available which are not there in linearity. When you study the stress strain graph of mild steel, you must have seen that there is a proportional zone and after that there is a plastic zone. So initially you have elastic zone, then you have plastic zone wherein there is a change of stress versus strain and it is not a straight line. So suppose if you want to plot the stress strain of a particular beam or ANSYS, then you need to take into consideration non-linear analysis. If you assume linear analysis and solve, you will only get the elastic part of the solution. Also, in non-linear analysis, there are large deformations that are encountered. You must have seen certain analysis wherein you get an error that there is large deformation and hence you cannot get the solution. At that time, you should give a option to the solver that it should consider large deformation, which means it should take non-linearity into account. So these are certain things which are there in FEA. If you use linear analysis, assume linear and go ahead, you will not get proper solution. Also, sometimes when you choose a material in ANSYS, you will assume that the material is linear and you do not incorporate the non-linear behavior into it. At that time also you will get error in your solution. But there is a reason why we prefer using linear over non-linear. That is, non-linear analysis takes a lot of time to get the solution. It is possible that it can go up to half an hour at times, even with good processors. The reason is it takes time to give you solution. So when you have a computationally demanding solution, at that time you need to have a good processor. So that's why we prefer going for linear and avoid non-linearity. But if you assume linear and avoid non-linear, then you will not get the correct solution in FEA. Mesh sensitivity. FEA results can be sensitive to the quality of mesh used. Poorly generated or distorted mesh elements may lead to inaccurate results. Mesh refinement is often necessary, but it increases computational requirements. You can go through the video that I have created, wherein you will see that if you create a coarse mesh, that is the size of the mesh is quite large, you will get a particular result. But as you keep on increasing the number of meshes, that is from coarse, when you go towards fine mesh and you increase the number of nodes and elements, what happens is you get better results. By better results, I mean, suppose if you are supposed to get a stress value of 56 Newton per mm square, if you use coarse mesh, you will get the result as 54.5. Suppose if you use medium mesh, you may go up to 54.7. If you use fine mesh, you may get a result of 55.5, which is going closer to your exact value. That is nothing but your better results. And mesh sensitivity here means that if you are giving better meshing, you will get better solution. But when you increase the number of nodes and elements, what happens is the device that you're using for running the software will take a lot of time to give you solution. So in that case, you need to have a very good processor, high-end processor, or it will take a really long time and sometimes the PC even gets hanged for a real long duration. So computational requirements are very important when you talk about good meshing. Modeling simplifications. Engineers must make simplifications when creating finite element models. These simplifications may neglect certain aspects of the real world behavior, potentially leading to discrepancies between the model and actual conditions. This is a very tricky thing. If you have a very complex model, it is difficult to design and then analyze. Also, sometimes when you're trying to mesh a very complicated design, it is going to show you that the mesh has failed because there are certain parts which are so small that meshing is not possible, or you may have to give large size mesh, which means you will not get good solution. So in such situations, what we do is we try to simplify the model and make it such that meshing and other options are easily available. But when you go for simplification of the model and oversimplification of it can lead to bad solutions. So you need to strike a balance between what model you have to create and how much you can simplify it. Because after a point, oversimplification will lead to errors in your solution. And you will get results which are not close to the readings which you have got experimentally. Inaccurate boundary conditions. Precise definition of boundary conditions is crucial for accurate results. Errors in specifying constraints or loads can significantly impact the analysis outcomes. So you need to be very careful when you are giving boundary conditions. If you give any wrong boundary condition or the area that you select for applying the boundary condition is wrong, then obviously you will get wrong results. So this is a disadvantage in terms of understanding of people who are using the software. So you need to be very careful in understanding the basics and then use the boundary conditions. Computational intensity. FEA can be computationally demanding, especially for large and complex models or problems involving multiple physics. High computational requirements may necessitate the use of powerful computing resources. Computational intensity means what is the type of processor that you are using. If you have a large and a complex model, then you need to have a good processor. Also, if you are going for multi-physics, which means you are first doing a structure analysis, then a thermal analysis, and then maybe some other type of analysis on the same body, in that case, you need to have a good processor, or else your device will go in the hang mode and you may get the results after an indefinite time, which you cannot figure out. Model validation challenges. Validating a FEA result can be challenging, especially when experimental data is limited or unavailable. It is important to validate the model against physical tests to ensure its accuracy. So at times you will have to use experimental data for verifying the results that you have got through FEA. It is possible that you may have got a result which is not correct. So at that time you need to have some data either in the form of theory or some experimental data and then validate your results obtained. Only then you can say that your answers are accurate. User expertise. Effective use of FEA requires a certain level of expertise in both the software tools and engineering principles. Misinterpretation of results or improper use of the software can lead to incorrect conclusions. So when you are using the software, you need to have certain level of understanding of the basics of the subject and also of the software. Or else it is difficult to use the tool because what results you obtain needs to be interpreted correctly. If you don't interpret the results correctly and you just get the colorful result, it is of no use. Sensitivity to input parameters. FEA results can be sensitive to input parameters such as material properties, boundary conditions, and loading. Small changes in these parameters can sometimes result in significant variations in outcomes. You need to be very careful when you are using a particular material property, boundary condition, or loading that you have applied to your model. In case you make any changes to it, which could be right or wrong, it could lead to different type of results which you should be able to interpret. Whether you get a correct result or you get a wrong result, at least you should know what result you have obtained. Computational cost. Performing high fidelity analysis with fine meshes and complex physics can be computationally expensive and time consuming. This can be a limitation, especially when quick turnaround is required. So, say you want to produce an output very fast with good amount of accuracy, you need to have better processor, which is definitely expensive, and also it will be time consuming because you are using fine meshes and you can use complex physics. So, at that time, you should be in a situation to have the hardware available, allocate the time required, and also bear with the expenses. So this is another disadvantage of FE. Limited by available software. The accuracy and capabilities of FE are limited by the features and algorithms implemented in a specific software package being used. Different software tools may yield different results for the same problem. If you compare a particular beam analysis in ANSYS and you use another software, say you're using NISA, you will get two different type of results. For example, by exact solution, you should get the answer as 55 Newton per mm square for the stress value. But by using NISA, you will get the answer as say 54.2, and by using ANSYS, you may get 54.5. Now, both the answers are close, but they'll be different. So, you obviously do not purchase two different softwares in the same company and compare the answers and then give it. So, maybe if you have taken NISA, you will get 54.2, and if you take answers, you will get 54.5. When I get answer closer to the exact solution, I will easily say that it is correct. But suppose if it is little far away from the solution, then you should be in a position to interpret as to what should be the domain that is acceptable for using the model that you have made. This is another disadvantage of FEA, that is what kind of software you are using. You may or may not get close answers all the time, but it is not related to NISA or ANSYS that I am saying. It could be vice versa as well in different situations. It is possible that sometimes one software gives you a better solution, and at the other time, the other software is giving you a better solution. So it is not a software specific error. It is just that what kind of mathematical calculation is used at the backend. Accordingly, they are going to give you solution. Dynamic analysis challenges. Analyzing dynamic behavior such as vibrations and transient responses can be complex and requires a good understanding of dynamic analysis principles. The accuracy of dynamic simulations may be influenced by the assumptions made. So, dynamic analysis is again a very important aspect of ANSYS. It is difficult to solve and interpret. It is not as easy as any steady state analysis that you do. So you need to have a good expertise in the field of whatever analysis you're doing. Say you're doing a structural analysis, or you're doing a thermal analysis, or any kind of vibration analysis, then you should have good understanding of the subject itself to be able to interpret what results you have got. Lastly, we'll discuss some key points of this lecture. Despite these limitations, when used judiciously and with a clear understanding of its capabilities and limitations, FEA remains a powerful tool for engineering analysis and design. Engineers should carefully consider the specific requirements of their problem and validate their models to ensure reliable results. You need to be careful as to what you want as the solution. You should have a basic understanding of the subject before using the software. Just using the software for the sake of it and getting some colorful results is not going to help. You should have a basic understanding of what you are trying to analyze. And basic concepts, as people always say, is something which is absolutely essential. If you don't know the basic concepts and you just try to get some results by giving some boundary conditions, and you can take the boundary condition from anywhere. Maybe the boundary condition is correct, the result is correct, but the most important part is the interpretation of it. So, with this, I end the session. I hope you have understood the lecture. If you have any doubts, please write to me in the comment section. Don't forget to like, share, and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.